So this is the Lewis structure, but this is not the molecular geometry or the 3D drawings. So that's what we're going to do. So we have an NH2, CH2, COOH. That's our.
Oh, that's the OH is going there?
Yeah. And so when we look at the nitrogen, I see this is a tetrahedral, e.g. electron geometry. And so I have a choice then. I have 3 bonds and 1 lone pair. When I have 3 bonds and 1 lone pair, the molecular geometry comes out to trigonal pyramidal. And so the easiest way to draw trigonal pyramidal is put the lone pair in the plane straight up, and then one of the bonds at a 109 angle here, another bond here wedged out, and another bond here like this. So I'll put the 2 hydrogens down here on the left. And so this shows the trigonal pyramidal geometry for this. And so what people often do when on like tests, because what a lot of students do is you're not allowed model kits on exams, a lot of exams. So people bring a whole bunch of pencils, and so on tests you'll see people with pencils in their hands like this, trying to, because sometimes the visualizing these things can be difficult because the molecules get kind of big and complex, so they'll do something like this. So if I do something like this, then this is the lone pair, and so this would be the electron geometry, and the molecular geometry we're just looking at bonded atoms, and so this would be the trigonal pyramidal arrangement here for the electron geometry. One hydrogen coming out, the other coming in. Okay, then we go on to the next. This one is going to be tetrahedral. Well, actually, we could stop here and just do this. So the EG is tetrahedral. The MG is trigonal pyramidal, and the angle, the angle here should be 109.5. But we're going to say it's going to be distorted. It's going to be distorted to about what? 107. Yeah, 107. Okay, then we go to this carbon. This carbon is tetrahedral with 4 single bonds. So if it's tetrahedral with 4 single bonds, what we want to do is we want to zigzag. So nitrogen, carbon, carbon. We're going to zigzag this. So this is going to go to carbon here, like this. And then we'll have a hydrogen come out. Now when we do this, we're going to put 1 hydrogen down here and another wedged here. And so it should match this, What I noticed what a lot of people did was they flipped this, but if you're looking at this perspective, it's got to have the same orientation here and here. And so the top is dashed, the bottom is wedged. The top here is dashed, the bottom is wedged. So it should be consistent. And some people inverted it here.
Yes, sir. Why do when you have your hydrogen, you have 4 lines right there? What are those 4 lines for?
These ones here?
Yes.
Those ones are to indicate that it's being projected into the board. And so it's going to look like this. You have 2 in the plane like this in tetrahedral. And that means 1 sticks out, that's the wedge, and the other sticks into the plane. That would be the dash.
So the solid lines on the plane, the wedges are out, the dashes are in.
Right. The wedge, these are in the plane. This one sticks out, this one goes in. Tetrahedral is always 2 in the plane, 1 sticking out, 1 going in.
Does it matter where you put them?
It does matter. So for example, like this is a common mistake. I see this all the time. Could it look like that? No. I mean, no, it can't look like that, because if you tried to model that with pens or pencils or sticks, it's not going to look tetrahedral. But if you put 2 like this, and then you have 1 going up like this, and then 1 going down like this, it doesn't quite work out.
What if you're saying it's going like out that way? Like it's like you're looking at it like book base, sticky bars out there.
No. in other words, what you can do is you can just build a little tetrahedral and then orient it in different configurations, and it won't come out like that. The only way you can do that is, the easiest way to do that is with models. And so if you build a model, you'll see there's no way you can make it look like that. No way. And so just build it and then see. All right, so this carbon here, the electron pair geometry is tetrahedral. The molecular geometry is tetrahedral, and the angles here should not be distorted. Should all be 109.5. Okay, then we go to this carbon here. What is this carbon here?
It's a trigonal planar.
Trigonal planar. And so it's going to have one double bond and one single bond. So where should we put the double bond and the single bond? Well, the single bond coming down here should continue the chain. And so this single bond continues the chain, so we should go to this oxygen here. And the double bond should go straight up here, like this. And the angles here should be what? 120. 120. Now, I want, for the lone pairs on central atoms, I want you to show me the relative position of the lone pairs. The lone pairs on the terminal atoms, you don't have to. You don't have to show me, but some people did show me. And they showed me wrong. And so, what should I do? Should I take off points for that?
You should encourage them to being brave.
Okay, I shouldn't take off points for that then.
Learning is about making mistakes.
But it's about being told when you're making mistakes.
Yeah, well, I'm not going to take off. I'm going to circle it and just, you should note that this oxygen has how many lone pairs? 2 lone pairs and a double bond. So this oxygen should be trigonal planar. If it's trigonal planar, then it's all on the same plane. So there should be a lone pair here at about a 120 angle, and then another lone pair here at about a 120 angle. And so some people made the lone pair come out and come in, that kind of stuff. So it was wrong, but it's okay. For terminal atoms, for central atoms, I need to see it. And so for central atoms, we have a choice. We have 2 bonds here and 2 lone pairs. And so typically what I do is I try to make as many bonds in the plane. This one I didn't. I could have put 2 bonds in the plane, and that's okay, you could do that. But the only reason I didn't put 2 bonds in the plane was to show this triangular pyramid standing upright rather than tilted on its side or upside down. Over here, I want to put 2 bonds in the plane, so I'm going to just continue the zigzag here. And this zigzag, you know, it's not, there's always this twisting around, so this is not rigid. The molecule's not rigid, except double bond. Double bonds are rigid. But this is flopping around like they say like a wet noodle or something like that. So it's not rigid, it's not fixed. So if we put the 2 bonds in the plane, where are the lone pairs?
You're going to be sticking with the wedge.
Yeah, one is going to wedge out like this. And so if I have one wedging out, where should I draw the dashed one? Should I draw the dashed one on the right side or on the left side, or does it matter? On the left side, because I want to be consistent here. I have the wedge here, the dash, and therefore the dashed lone pair should be on the left. So I maintain the same perspective. That makes sense. All right, and so when we go to this carbon here, the EG is trigonal planar, and the MG is trigonal planar, and the angle here is 120 degrees, but it's going to be distorted.
Oh, yeah, that's.
Yeah, if we look at this angle here, it should be expanded, that is, or contracted.
Expanded.
Yeah, and it's going to be roughly what? Yeah, 122. This one here,
About the same.
about the same, 122. And then these angles have to add up to 360, so that means this bottom angle's got to be 116. And so it's going to be a little bit distorted because of the double bond's going to have greater repulsions associated with it. Now, I have three ways of drawing lone pairs. Like this is in the plane, this is out of the plane, this is going underneath or inside. So within, coming out in front, and going in back. Anyway, going to this oxygen here, the EG or EPG is tetrahedral. The MG is MG is not tetrahedral. MG is.
I would have thought it
You
was
just get rid of the.
Bent?
Yeah, then it looks bent. The lone pairs are there, and that's what's causing it to be bent. But when we're looking at the MG, we just ignore those. And the angle,
it's gonna be like.
it should be 109.5, but it's going to be distorted to about what, 105.
Why is that one distorted?
Because two lone pairs,
Oh, yeah.
so about 105.
You see, 109.5 times 4 is.
Well, each lone pair compresses at about 2 degrees. So first lone pair goes to 107, like over here. First lone pair goes to 107. Second lone pair is going to go to 105. All right, any questions on this? No. Any questions on chapter 13? No. All right, now we're to chapter 14. Chapter 14 deals with gases part 2. Yeah, gases part 2. We're going to do two more laws here. One is Avogadro's law. Avogadro's law just says that the amount of gas depends on the moles or the molecules.
I have a question about.
Oh, it's okay if you have a question.
Just like this initial in front of the problem, N on the, at the gas pressure.
Yeah, each of those represents something. Like today, we're going to do the ideal gas law. PV equals nRT.
Oh, yeah, I did that one.
P is the pressure, V is the volume, N is the number of moles, T is the temperature, and R is the gas constant. We're going to do that in just a minute. But first, this is the ideal gas law. But before we get there, we're going to do Avogadro's law. Avogadro's law just says that the volume is proportional to the number of moles. The more moles of gas we have, the bigger the volume. So that's all. It's directly proportional. And so with Avogadro's law, we could use it like this. You know, if we look at a chemical reaction, this is Avogadro's. This chemical reaction is here. We have one oxygen. Okay, that's 1 mole of oxygen plus 2 hydrogens. Well, that would be 2 moles of hydrogen. And so 1 mole of oxygen plus 2 moles of hydrogen yields 2 moles of water. Okay, this water is going to be gaseous water in this case here. And so we have a mole ratio. So the mole ratio is 1 to 2 to 2 mole ratio. So every 1 oxygen needs 2 hydrogens, it produces 2 waters. Well, it turns out the volume ratio is the same. And so the way we could use the mole ratio is like this. Let's say I had 2 moles of oxygen. If I have 2 moles of oxygen, how many moles of hydrogen do I need? 4, double that. And how many moles of water will I produce? 4. Be double. So it'd be 2, 4, 4 is the mole ratio. For the volume ratios, it's the same because the volume is going to be directly proportional to the moles. So the more moles. The volume ratio is if we're dealing with fixed. Fixed means constant pressure and temperature. As long as we don't mess with the temperature and pressure, then the volume ratio will be the same. So the volume ratio is going to be a 1:2 volume ratio. So we could use any volume units we want. So if I had 1 gallon of oxygen gas, how many gallons of hydrogen gas? I would need 2 gallons of hydrogen, and I'd produce 2 gallons of H2O gas steam, actually. As long as the pressure and the temperature are fixed. And so we can use this. And so that's what they did here. So rather than gallons, they used milliliters. So if I have 50 milliliters of O2, 50 milliliters of O2 requires how many milliliters of hydrogen? 100, and that's going to produce 100 milliliters of H2O gas. The interesting thing about Avogadro's law is it doesn't depend on what the gas is. You know, it doesn't matter if it's oxygen, hydrogen, or water vapor. The particles themselves are extremely small. So I know hydrogen forms smaller molecules than oxygen, but that's not going to change it. You know, so for example, if I have 4 O2 molecules here, and I have 8 H2 molecules here, 8 H2 molecules will take twice the volume as 4 O2 molecules, even though the H2 molecules are smaller. And so it just depends on the number of particles, not the actual size of the particles. The actual size of the particles is very small. Gases are mostly empty space. And so 4 O2 molecules reacts with 8 H2 molecules to form 8 H2O molecules. And 8 H2O molecules will take up the same volume as the 8 H2 molecules here. And so Avogadro's law is like that. Now, what we're going to do is we're going to go back to the previous laws. Do you remember the previous laws? Charles' law was one, and Boyle's law. And so if we take Charles, yeah. Oh, I forgot. This is another illustration. And so the volume is directly proportional to the number of moles. So if I have 3 molecules or particles here, if I double it and go to 6, it's going to take twice the volume. If I triple it and go to 9, it's going to take 3 times the volume here. As long as the temperature and pressure are the same in all those. Now, if I double it and keep the volume fixed, let's say, you know, this lid can slide up and down. The pressure is maintained constant because there's weight of the atmosphere here and the weight of the gas in here. Once they match, that's the volume. So if I double it here, the lid's going to increase. But if I fix the lid down here, then the pressure would have doubled. You know, if I kept the volume constant, it would have tripled the last scenario. But I maintained constant pressure by allowing this lid to move up and down. In other words, I'll allow the volume to expand and contract. So if we combine Charles' law, Boyle's law, and Avogadro's law, we get the ideal gas law. So the first thing is, what is an ideal gas? An ideal gas is a hypothetical gas that behaves like a gas under all conditions. And so if we look at this, oxygen is pretty ideal and hydrogen is pretty ideal. And so these are both fairly ideal gases. Do you know what the most ideal gas is? Helium. Helium is the most ideal gas. But steam, is steam an ideal gas? Is steam an ideal? Steam is not such a great gas. Do you know why? Because steam doesn't like to stay a gas. When we get to 100 degrees C, what does steam do? Well, at 100 degrees C, steam will condense back into a liquid. And so it doesn't stay a gas.
Didn't they used to use steam for power?
Yeah. They still do.
They concealed it.
In nuclear power plants, they use steam. Yeah. But steam is not such an ideal gas. Helium stays a gas all the way to, helium's pretty ideal. Helium's the most ideal gas that we have on the periodic table, but it isn't perfectly ideal because you know what happens at 4 Kelvin? Helium condenses into a liquid, so it doesn't stay a gas. And so let's do we're going to do a little demonstration, I think, for steam. Except I forgot one thing.
Safety law.
Yeah. So I'll do the demonstration in a minute, right after our break. Okay, so what we're going to do is we're going to combine these. You don't have to worry about this, and then we're going to come up with the ideal gas law. The ideal gas law describes the gas. This is the ideal gas law here. And so the ideal gas law just describes the physical characteristics of pressure, volume, amount, and temperature. You know, these things are all related by R. R is the gas constant. And so, let's see. What did I do here? Pressure, what units do we usually use for pressure? Atmospheres. Volume, what units do we usually use for volume? Milliliters or liters? We'll probably use liters because we'll be going to bigger volumes. And moles, this is just moles, which would be moles. T, Kelvin. And so R is going to be dictated. We have different values of R depending on the units. The most common units are going to result in an R value that's equal to 0.08206. This is before sig figs. That's not exact. 0.08206 liters times atmosphere per mole Kelvin. That's our
The book gave us 0.0821. Do you want to just use that one?
No, I don't want you to use that one because what's going to happen is, I know the book is going to give you 0.0821, which is good to, not 4 sig figs, it's good to 3 sig figs. But that's our book, and then Chem 1A, they're going to require you to memorize it to 4 sig figs. So rather than memorizing it to 3 sig figs now and then re-memorizing it to 4 sig figs next chemistry class, it's just might as well just memorize it to 4 sig figs. But you don't have to memorize it because this will be given anyway. I'll give it to you. Look at it. We're just going to always get in the habit of using 4 sig figs for R rather than 3 sig figs. All right, so how are we going to use it? Well, in this example, they want to show how R is determined. So in this example, we can determine R experimentally. We can determine R experimentally by measuring the pressure, the volume, the number of moles, and the temperature. And so in this particular example, they measured the number of moles, 0.1000 mole. This is helium. Now, the ideal gas law doesn't ask you what gas we're dealing with, helium, oxygen, nitrogen, whatever. Any gas, it works as long as it's relatively ideal. So 0.1000 mole sample of helium, helium's the most ideal, so no problem with that, is placed in a piston and heated to 25.00 degrees C or 298.15 Kelvin. The volume is adjusted to 4.600 liters and the resulting pressure is measured at 0.5319 atmospheres. Use these data to determine R. And so all we do is plug in the pressure in atmospheres, the volume in liters, and in moles, and T in Kelvin. So we plug that into this equation here and solve for R. And so they get R is equal to, and they're getting 4 sig figs here. We're allowed 4 sig figs. 0.08206. And I do liters atmosphere mole Kelvin, but it doesn't matter. So 0.08206 liters atmosphere per mole Kelvin. And so R can be determined empirically, and it's always, this ratio is always a constant. The pressure volume divided by NT. So it's in that constant. We don't use ideal gas law to solve for R. Usually you're given R. So the most common application of this is to determine a single variable. That is the ideal gas equation, determination of a single variable. This slide is divided into two parts. I tend to do here. But basically, determination of a single variable is pressure, volume, and T, or what's required to characterize a gas. And so if we want the pressure, then we need to measure the volume, the moles, and the temperature. If we want the moles, then we'll have to measure the other three. So given three of them, find the fourth one. And so that's a typical problem. So let's take a look at this one. What is the pressure in atmospheres in a helium-filled 0.77 liter balloon if it contains 1.0 grams of gas at 20 degrees C?
RTO.
Yeah. And so pressure is nRT over V. Pressure is nRT over V. And so we'll need the number of moles. Are we given the number of moles?
No.
No. But we're given the amount of helium. The amount of helium is 1.0 grams of helium. So if we go from grams of helium to moles of helium, that'll work. And so we'll just plug in the molar mass. 1 mole of helium weighs how much?
1.01.
4.0 helium. Yeah.
4.00.
4.00 grams. And so if we're given 2 sig figs, then our molar mass should be 3. So that's okay. And so this comes out to 0.250 moles of helium. So we have the moles of helium. We have R over there. What's the temperature?
It's Celsius, but we can change it to Kelvin.
Yeah.
So 273, but no.
273 plus 22 would give us 295 Kelvin. What's the volume?
0.77 liters.
0.77 liters. So we just plug those numbers in. Oh, one thing your book loves to do, your book loves to come up and derive other equations. So for example, if we're not given the moles, then they'd like to come up with a new equation, you know, here, but I don't like that. I'd much rather than remembering a whole bunch of different equations, I'd just rather remember one equation and then convert everything to the right unit. And so plugging in all the numbers here, we get 7.9 atmospheres. One thing I don't like is your book doesn't show the rounding step. This actually comes out to 7.85 atmospheres, which rounds to 7.9 atmospheres. So I'd like to show one additional step, the rounding step. That must be one strong balloon because, you know, that's almost like 8 atmospheres.
What?
The pressure. 8 atmospheres of pressure. 8 atmospheres of pressure. If you think about it, let's say if you're standing next to the pool, what's the pressure? The air pressure. Next to the pool. Air pressure is about 1 atmosphere, right? What if you jump inside the pool? If you jump inside the pool, then you have 1 atmosphere of air plus however much the water weighs. And so let's say you go like 9 feet deep. If you go 9 feet deep, that's about 1/3 of an atmosphere. Yeah, less than 1/3 of an atmosphere, 9 or 10 feet. And so if you go 9 feet deep, then you have 1 atmosphere of air and about 0.3 atmospheres of water. And so you're about 1.3 atmospheres. In order to go 2 atmospheres, that is 1 atmosphere of air and 1 atmosphere of water, makes a total of 2 atmospheres of pressure. How deep underwater do you have to go?
27.
About 30 feet.
About 30.
Yeah, so you go about 30 feet deep and then you're at 2 atmospheres of pressure. Well, this balloon's at 8 atmospheres. That's pretty horrendous. I mean, it's got to be a strong balloon.
It's not that deep.
It's a lot of pressure.
It is.
30 feet is not that deep? That's for me. I don't like going deeper than 6 feet or something.
Don't people go like those professional, they'll dive all the way down to this deep.
The keyword though is professional. When people have to pay you to do something, that's how you know.
Bro, that's professionals do. You do it.
I could do it.
I would never stop.
You just gotta collapse your lungs. You just gotta let out the air.
No.
Hold your breath.
Well, then they have the deep sea divers. They don't even breathe like gases. They breathe liquid.
What do you mean?
The pressures are so high. A lot of gases will
Oh,
liquefy.
we could look at an example. It's 271.2 feet of H2O that you have above you have 8 atmospheres.
271 feet.
Yeah,
271 feet.
No, that
So-
is deep.
Of water
That
on
is
top of
deep.
you.
Yeah, that would be 8 atmospheres of pressure. 8 atmospheres of pressure is a lot of pressure.
Okay, so
How
one
many
atmosphere is 30 feet.
Try. I wouldn't even make it halfway.
Well, anyways, we'll stop here. We're gonna take a break, and then I'll show you my.